Alright, draft physics video. Another effort at human communication. Yes, it's fundamentally impossible. But we'll keep trying for the hell of it. There's no other game to play. Anyway, can't get around that argument. It's another really good argument. So, different things. Got some comments to deal with. This dissident science guy, I watched the Particle Guru, which is his father, there, and sort of got the outline of their theory, and close, but no cigar, as they say. But it is very close in terms of they were heading the right way, and they got rid of the wrong things. But anyway. So first, I guess a little bit on the lensing thing. Just trying to find a better way to explain it, and just because it's just fundamental physics, and Einstein would have said, "Oh yeah, it's no big deal lensing," if it wasn't really hard to do, bending light. So it's a very small thing, moving very fast. So let's preview the circumstance. So I really shouldn't even have to make these arguments about some of this stuff. Like for instance, the flatness of the galaxy and how we're looking at lensing images going through the thinness of the galaxy. So when Piro says things like, "Well, the photon's in the gravity for billions of years," it's going the shortest distance by the galaxy, and when the galaxy is this way, pi in your face, the light's going through really thin amount of gravity, where if it traveled this way, across the top of the galaxy, so to speak, it would be in that, and then it would be in the gravity of a very long time. So if these lensing images were actually on galaxies on edge, they would make more sense, because that would be a very long distance. So anyway, their argument is so we have a object, let's say a galaxy, and it's that small compared to the place where we're seeing the Einstein ring, let's say, the image thingy. All right, so let's just say that's 9 radiuses wide to that point. So the idea is that they're saying, because this is a long distance, they're not even thinking about the right way, right? This is the real distance. It says you can't draw this stuff on a piece of paper quite right, but the real distance, you have to think about a line going this way, because you're going through that side of the galaxy. You're not going across the galaxy. So when Piro says the galaxy is 200,000 light years across, well, yeah, that's this way, but you're traveling this way. You're just going through the little edge of it. But anyway, let's just for the sake of argument. So the point is that they're saying, and the lensing has to be rather significant. So as much as people say it's a tiny bend, it's really not. It's a significant difference. The angle difference is significant to get to Earth, to be viewed at the wrong place. So I figure we'll just do a tiny bit of math here. The way I've come to think of it now, just because it's more, my last video there was a little bit of an error in there. I went to 16, and I should have gone to 9, as 2 radiuses is 9 times. But anyway, when they say 1 over r squared, I think a better way to write that, see, that's really the total distance. So it's not really the radius anymore, the r. The r is this radius of the new thing you're measuring. It's that radius, and assessing the mass of that radius, you end up with assessing it just as the mass of the little object inside of here, so it becomes a very undense object. So anyway, a way I thought to think of it was it's like 1 over r number squared, the number of radiuses squared, is a better way to think about it. So if this lensing event was, say, 9 radiuses of the object, then that would be, the squared would be 81. So it would be 81 times weaker gravity. And so if you go depending on where you go away, how far you go away from something. And so another thing to understand, so this distance, let's say if you went right next to the galaxy, this would be your line. And if you go past the whole roundness of this galaxy, like I said, they're not doing that, right? If you went past the whole size of the galaxy, the flat galaxy, then you'd have a very long path. But we're being fooled because in the real circumstance, it's going in and out of the paper here. You can use a little X or O symbol whether it's going in or out, but I'm just saying it's going through this little line here. So anyway, but I don't want to get lost in that technical point. So let's just use this as a proportional number. So you could say that if you called this the line of gravitational influence, this line's only going to be 9 times bigger than that line. Just like the radius is only 9 times more radius. So you only gain 9. So, the number you have here is whatever the gravitational constant is. So we just call it, GC. And you have it, here, it's the bottom line number is just going to be 9. And at your new location, it's going to be GC divided by 81. So, you've really diminished the gravitational effect. The amount of tons actually hitting the thing is going to be much, much less. So, and even if I let you double that or triple that, and I said, here, I'll give you time dilation too. I'll give you another one for time dilation. I'll give you 2 more for time dilation. Even if I give you that many chances to go back and forth through the gravity, you're still going to be half as much gravity as you got on this much shorter line very close. So this much shorter line very close, you collect so much more bendable influence than you ever do way out here. And people just have to appreciate what that square means. I mean, it's the difference between 81 and 9. That's how big the difference is. That's how much weaker it is out here. Alright, well, I'm not entirely satisfied with that, but it's going to have to do. I don't want to spend too much time on this stuff. I'm just amazed that not one of you cranks has the integrity to go on Piro's board and tell him he did it wrong. He's wrong. I just can't believe none of you understand how gravity works at all. I mean, I find it amazing. It's just absolutely amazing. But it just is demonstrating something, I suppose, in terms of that's how deep this your problem with psychology is. Here, Piro's doing this psychobabble game, but I mean, it really applies to you people because you're showing absolutely no intellectual integrity to defend just stupid notions. Why do you think they use dark matter as explanations, the real scientists? Do you think they want to use dark matter to explain lensing? They don't want to. They're doing it because they have to, because they know the math doesn't work. Just amazing. Anyway, alright, so there's some asshole called Pennywise who, yes, you're of course blocked, you stupid, dirty, stinking, rotten, crappy, slimy piece of crap. I mean, just uselessly arrogant, rude, and there's just nothing. There's no counter argument that is at all rational. So here's one of his comments. No, not everything in space is perfectly round, nebulous. Alright, so I clearly said in my video, strong gravity. I used analogies in my gravity that, oh yes, you could take 2 batteries and put them in space and just kind of push them next to each other so they stick to each other. And yeah, they're not going to go round because they don't have enough gravity to force themselves to go round. But anything that gets any size to it is going to tend to go round. Every time it gets hit and gets heating up and gets molten a little, every single time it gets a little bit liquid, it's going to go round. Every single time. So that's what gravity does. And if you did it with water drops or jello or vomit in space, it'll tend to go round. And that's the fact, because that's what gravity does. You're wrong. You're an idiot. So he says nebulas, they're not round, right? So nebulas are another example of something that's incredibly weak gravity. Whatever the surface would be on a nebula, okay, there's no strong gravity. Again, it's full of empty space. It's lighter than rice cakes. I mean, I just don't know how you could be this stupid. It has no center of gravity. It has so little gravity. Oh, anyway, they're not round. Most galaxies aren't round either. No, well, most galaxies are spherical, so that's just a pile of shit. So that's not even close to an accurate statement. Most galaxies are symmetrical at best. There's no way you could justify a statement. Most galaxies are what? Shaped like Donald Duck? No, they're not. I mean, it's just a stupid statement. Alright, so delete that. In my humble opinion, the way you tell if something is an explosion is if it looks anything at all like an explosion. So again, I mean, this doesn't take much. I said smoke rings. I mean, anybody who's seen a cannon fired, or even guns, I don't know, some guns, shotguns. Smoke rings are a common event, and clearly, if you've seen video of an explosion or something, you can see, like from overhead, you'll see that it has a real bullseye look to it. So again, what's your argument? I mean, it's a silly. You're just arguing for the sake of arguing. I mean, it's not rational arguments. It's not a disputable point that explosions tend to be symmetrical. Alright. Scientists aren't as lazy as you. Again, it's not an argument. You're again worrying about the messenger, not the message. Again, you're not arguing the subject, you're arguing personality. So I'd say that most trolls don't have as small a penis as you. So maybe you should just walk off somewhere and get depressed. Because yes, you are a miserably ugly and smelly piece of shit. Unlike you, they read books. Again, books written by the Pope. And they study composition of stars. And so again, he's saying there's something to study here where you'll find out that the further away you go from something gravitational, the more likely you are to get bent by it. When in fact, no, you're less likely to get bent by it. And resulting spectra, well, that means nothing. And they understand that statistically, even if several stars formed near each other, no, they formed in the same solar system, just like the planets formed in the same solar system here, and they would share the same chemistry if, say, that solar system, which kind of obviously in the Einstein rings case, I think, is kind of obvious, that planets aren't really an issue. These are the suns that are formed. So anyway, even if several stars formed near each other, they'd still have different spectrums. Okay, so why don't you just prove that the simple way, right? There's many binary systems, right? Solar systems. They say that anyway. They say a huge number, I don't know what percentage, 10% of the stars in the sky are part of binary systems. So why don't you just show me a binary system where the two stars in the binary system have a different pH or something, have a different signature. Because I bet you they have the same signature. So I think you're going to lose that argument. Even if several stars form near each other, like I said, we're talking about 4, they'd still have different spectrums. So you say so. I'll source that somewhere. Where do you get that from? You know how stars are formed in binary systems. You have the fact book. You read the book. Because they have pictures of that somewhere. In much the same way that even galactic twins have different fingerprints. Galactic twins, genetic twins have this different fingerprints. So yes, but nothing else. They have the same immune system. They have the same epigenetic code. They have a million things that are identical about them, but you'll just find the one thing that might be different. Wow, how interesting is that? Oh, not interesting at all. I mean, really. So you think that's a point? That because the two zygotes wrinkle different, as they're maturing, somehow that means there's enough difference in genetic twins to sit there and tell somebody else that the two stars that were formed in the same swirl of space dust are somehow fundamentally different. So different that we can tell from millions of light years away. Yeah, fuck you. Alright, absolute bullshit, he says. The gravity does fucking add up. Add up to what? How do you add nothing plus nothing plus nothing equals nothing. Never heard that song? I mean, it's nothing. The amount of gravity is 0.0000000000001, let's say. So you can add that to each other forever almost, and it's going to take an awful long time to collect enough to have any hope of bending light. And again, I don't even know what you think bending light does. I mean, that the photon is just sitting in this very weak, slope, and it's just slowly creeping. Or however you think gravity works. It's following the geometry. And somehow each photon in that little tiny bit of gravity, that if you quantized it would mean it would take full impacts. It's just really getting hit by bullets, but you don't get hit by too many of them. That if they were just getting hit by a quantized gravity, that's why they'll never match gravity to quantum mechanics, is because they'll never quantize gravity by your own words now. Means that the photons would never be disturbed by the same amount. And if gravity worked the way you think it does, where all these weak gravities were moving photons all over the place, then we'd never be able to see a galaxy 10 billion light years away, because the photons would have gotten destroyed by all the gravitational influences they had traveled through. But anyway, it's just stupid. There's nothing to add up. Einstein's math says so. You want to refute Einstein, why don't you refute Einstein on some message board somewhere and explain to them how Einstein was wrong. That you can have lensing far away from the sun. All you have to do is just spend more time in it. Anyway, the Earth would continue orbiting normally. Whatever. Okay, here, I'll have to go back. Add up, because if the sun collapsed into a black hole, well, we're not talking about that happening, that wouldn't affect the Earth. Yeah, well, you're going the wrong way, idiot. We're talking about going outside the gravity, not making the gravity stronger. And yes, it's true that you could make the sun smaller. If you didn't add any mass to the sun and you made it smaller, it would be exactly the same for us. But that's exactly my point. The thing you're saying is lensing is lighter than the sun. There's space in it. It's suns with a bunch of space. You see? It's lighter than a sun. So if you compressed it to its size of a real sun, it would be a tiny little thing. Really tiny. And that means you would be hundreds of radiuses away from it. So if a galaxy was as massive as a sun, it would be a tiny speck of a thing compared to what we see. And instead of being 9 radiuses away, you would be 490 or 7,646 radiuses away. And then your numbers would get insanely crazy in terms of how preposterous your delusion is that you can bend light in weak gravity. Alright, the Earth would continue to orbiting normally. If you got to within a radius of the sun from that black hole, the gravity you felt would be the exact same gravity you would feel if you were near the sun's surface. No, that's just not true. So if you compress the sun into a smaller thing and then just go a radius away, that gravity is going to be stronger, much stronger than the sun's gravity. You now have access to much stronger gravity. If you make the sun's volume smaller, it means you've made the sun more dense. It means that instead of 70 meters per second gravity on its surface, it might have 700 meters per second gravity on its surface. So you're wrong again. You'd feel, if you were near this, that's what everyone that took high school physics, this isn't high school physics, idiot, but whatever, and didn't sleep through it would be able to tell you. Well, I'm telling you, you're flatly wrong. You're an imbecile. You're an idiot. And it's really tragic that people can do that, can say things that just aren't true. It's like somebody like you arguing that humans existed at the same time as the dinosaurs or something. You're just arguing nonsense. The title of this is Horrible Video. The title of this horrible video is the epitome of irony. Yeah, right. No, it's a very accurate description of fanatic zealots who lie, cheat, and steal to defend their fantasy, their fable. And that's what you are. You slander Einstein, you ignore the mathematics you so revere. Here you are shitting on it. I mean, you assholes have been griping about how your math solves everything, and here you are saying, fuck the math. I don't want to hear any of that shit. I'm sorry, anyone that still listens to you and doesn't think you're lying is a moron. Doesn't think you're lying is a moron. Well, that wasn't too good. And doesn't think you're lying is a moron. Oh, you need a comma there, fella. To the 88th degree. Huh. Well, I'll just remind you that the gravity where Piro thinks he's going to get lensing is 81. Okay, times 2 weak. Alright, fuck you. Let's see. There's one last. Oh, here's another one of his stupid comments. Let's get him done with and then I'll block him. Do you get it that these galaxies are millions of light years wide, right? Well, do you get that if you see the galaxy this way, the flat plane of the galaxy, if you're seeing the spiral arms and such, that means that's not the way you're going through the galaxy. You're going through it this way, retard. It's not millions of light years across this way, Dumbo. Right, Dumbo? Did nobody explain this to you? Did nobody explain to you galaxies are flat? They're not spheres. Dumbo. You don't think the gravity could exert an influence over tens of millions of years. I don't think it can bend the light because, as Einstein's math demonstrates, it can't get the sufficient number of photons, the sufficient number of energy can't be collected because the gravity is 81 times too weak. 81 times too weak. Shit. Let's see. That's like saying, how could a small mammal ever evolve? So he keeps using analogies that are so distant from the subject. I mean, shit. Monkey evolution isn't exactly have much. I mean, it's a real stretch. Has nobody explained that to you? That it's a real stretch to compare galaxies to monkeys? How could a small mammal ever evolve into a tree-dwelling monkey? I can't. A small animal? I can see how lots of them would do that. I can see rats. I've seen rats living in trees. Called squirrels, idiot. I can't imagine that. Yeah, it's called millions of years. Shit for brains. So again, and it's called math. And if you did the math, or you had any respect for Einstein, you'd recognize that he wouldn't have told you you're only going to see lensing on the surface of very dense objects. Right, he was lying. Let's see. This is why these 7 years you spent watching physics lectures was wasted. Well, the time your mother spent carrying you was obviously wasted, because you're just a vile, disgusting bucket of puke. It's because you do your homework. It's because you didn't do your homework. Yeah, right. No, I didn't get indoctrinated like you into an insane fanatic for a science you don't even understand. Go read your Bible. Maybe people that get physics degrees from Yale, they have to do the math. Well, you're the one rejecting the math, so this is just so ironic out of your mouth. What math? Go show me the math that makes it possible. You spend 9 times more time in the gravity, and the gravity's 81 times weaker. So go ahead and explain to me how you have a better chance of lensing there. The gravity's 81 times weaker, and you're only going to spend 9 times longer in it. What the fuck makes you expect those of us that do get the math? Again, you don't get it. You step on it. You're using it for toilet paper right now, you fucking lunatic. That do understand how lensing works. Well, again, you don't understand. I'm not even going to read the rest of that. Fuck it. You're done. It's just too stupid. You're obviously an imbecile. You obviously haven't done any homework on the subject. Ever. Okay. And you see, he did something to... Oh, he puts Lawrence Krauss. He starts talking... anyway, it's a response to superior mind. I might as well read it. This is his last word here. So it doesn't bother you that all 4 stars supernovaed at exactly the same time. So he thinks that stars are formed because a supernova explodes and then contracts, and that's how the star was formed. Because the star blew up and then contracted. But stars don't form because the star supernovas, and then the material that is the consequence of that explosion, perhaps other stars even that might be influenced by that supernova, end up creating swirly bits. Or the things he called the nebula, which are kind of known for making stars also, that they would have all this dust that they're collecting. Through the weak gravity, the dust slowly collects. And that would be how the stars were formed, or are given birth to. So stars aren't all made by supernovas. They collect the dust from supernovas, but it's not the thing that creates new stars. So you don't even understand that. It does seem a little, it doesn't seem a little suspicious to you. Well, he's not as dumb as you. He doesn't think stars are made by a supernova. They contain the remnants of supernovas. You really think that they're all the same fucking time. That's what it says. You really think that they're all the same fucking time. You know what? You're intellectually lazy. You're retarded, so it doesn't matter. You did nothing but sit at home. It's just more nonsense. Forget it. I won't bother reading it. Yeah, it has no argument, so it's just got insults. Useless. I mean, his arguments are idiotic, so blah, 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 blah. Alright, so Mindless Marvels did leave a bunch of junk. It's probably worth going over some of it. I just don't know if I have time to do both things. Well, we'll just do this, and then if we don't get to the Hilster guy, that's it, David Hilster, then we'll get to him next time. Let's see. So he's being all polite and trying to form his question within the rules and blah 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 blah. So yes, take it to an extreme. Blah blah blah. I don't care though. Let's see. Hello. I would like to see what your theory predicts for the below scenarios. I am skeptical that your theory can reproduce some of these. Whatever. But they are very simple. So who knows? For some, these are images. For some, there are images provided, right? So I'll go to the images. Basically, I want to ask what happens, e.g., there's attraction, repulsion, etc., but I hope you can explain how your theory arrives at its answers. They'd be the most important part. Thank you very much. So, scenario 1, wire and magnet. Imagine a magnet with a north pole facing you. Place a horizontal wire between you and the magnet and let electrons run left to right. What happens to the wire? So this is just one of those simple arguments about when there's current running through a wire, how does it generate magnetism? I would imagine it's something like that. So here's the scenario. So the magnet's on end, but it's drawn very thin for whatever reason. So the north end of the magnet is facing here. There's a current. Well, it doesn't have any plus and minus signs here. And he has a little E, so the with a negative. So I assume he's saying this is the negative end and this is the positive end, and that current is running through the wire. And so the argument would be since this is the north end of the magnet, which way does the wire move? Maybe he's asking. The problem is you'd have to know what the voltage is, I think. I mean, you need a lot of amperage to do this experiment. But the idea would be, this is the, see, current and voltage go the opposite directions, so it gets very confusing. So let's establish what I mean, you should just put plus and minus, and then I can say, okay, so this is the end you're saying has too few electrons, and this is the minus end has too many electrons. So this is the minus, and this would be the plus then. So we have a current going this way, which means that the electrons are going that way, and the protons are going that way. So it means that the electrons are producing the force in this direction, mostly perpendicular, but kind of moving a little. Some of them going more this way. Okay, so if I could draw here, I would just draw it like hairs going a little bit at an angle. Because as the electrons move, they don't move perfectly straight, so some of these angles will be off. But the general idea is that the black force will be going this way, and the red force will be going this way. So the magnet wouldn't want to stay this way, it would want to turn, but I don't know what he asked exactly, because that magnet doesn't look like it's going to be very easy to do anything. Whether it would be attracted or repelled, it would be repelled, simply stated. If we assume the north side to be the electron side, the black side. So if the magnet's on its black side, the black force is coming out of the north side, and we have black force. Well, sorry, my mistake. The electrons emit red force, so they would attract. Sorry. I'd probably be better off if I drew it in red and black, and then you could understand what's happening. Yeah, maybe we'll do that. So when you have a wire, should have a neutral color for the wire. What's happening is if you have a voltage, it means you have a storage. You have too many electrons at the negative end. So you have we have to draw a symbol for something that's higher potential. Oh, HP. So this is the HP end, and this is the LP end, low potential. So there's too many electrons at this end, so the electrons are going to tend to move this way, which is essentially just meaning that the force is going to move that way. And so the movement will be in this direction by the electrons, because the force is going to move that way from the high potential where they've been compressed. So the electrons are pushed into each other. Their natural state is this more relaxed state, and now they're in this unnatural state, which means they have a high frequencies between them of impacts. They've got a lot of pressure. So now they're going to move as soon as they're given an opportunity to go through the wire. And when they do, they're going to release red force in tending to go in this kind of, it's perpendicular mostly, okay, but it is a moving force in the sense that it's perpendicular, but it has some angular momentum, so to speak, in this direction overall. So there's going to be more red going this way, and there'll be black going this way. And that'll be true for the entire length of the magnet, around both sides, the whole thing. So it will tend, if there's a north magnet this here, alright, so it's the black end, which is producing black, okay, there's going to be more attraction than repulsion. So the wire will be attracted to the north end of the magnet. Alright, so on to the next one. I mean, I suppose I could just look this stuff up and then give, fake the answers. But anyway, let's be real. Let's keep it real. Alright, wire. Imagine two vertical wires. What happens when you let current in both run in the same direction? Well, that one's too easy. They're in the same direction. Well, let's look at your image, but yeah, that one's just too easy. They're going to create magnets in the same orientation, which means they're going to repel each other substantially. So, oh yeah, he doesn't have a great drawing again. So they're both going the same way, and then when they're going different ways, it just creates two different magnets. So in this case, the electrons are moving this way. The protons essentially are moving the other way. You can think of it that way anyway. But the point is they're releasing their energy in these directions. So all the black is going to repel this way. So these two, and the reds are going to repel. So the two wires are going to run away from each other. And here they're going to have opposite polarities, which is going to mean they're the same as a regular magnet. So that one's too obvious. Alright, imagine a vertical wire, so wire and compass. Imagine a vertical wire with a compass placed next to it. What happens to the compass when I run electrons downward? Down, and then you want to know which way the needle points. You don't know about this one. Alright, okay, so this is the top view. So there's a wire going this way through the board. Which way does the compass move if you're going downward? Yeah, well, I don't know north or south. I can't tell you which way it's going to point. It depends on which way the current's going. So if the current's coming out of it, yeah. Yeah. Are you asking me to be able to tell you whether the north end of the compass is sensitive to black energy? I mean, electron sensitive? I guess that's what should be established before I did this, is I should establish what side of a magnet, the north or south pole, is the electron side and which one is the proton side. But let's just assume for the sake of argument that it is the north side is the electron side, which means that's radiating, the electrons are radiating the red force. So there would be attraction. So yes, it would probably point north. Alright, magnet and coil. I have a rectangular magnet with a north side facing up. Now suppose that I closed coil right above the magnet and keep it above the magnet. What happens in terms of current when I stretch the coil in the direction length of the magnet? So you're moving a coil over a magnet. Instead of moving a magnet over a coil, you're moving a coil over a magnet. Okay, I think. Alright, so he's moving a coil over one pole of the magnet. That I don't think will get you too far. So, I mean, you just one pole of the magnet is all black energy, Well, it's still going to move electrons in the conductor. So, yeah, you'll get some alternating current in the wire. Yeah. It'd work even better, though, if you had both poles of the magnet, like a horseshoe magnet or something. Alright, next, can magnet and comb. Can, magnet, and comb. Alright, so he doesn't have an image for this one. Place an aluminum can on a flat surface. Say I bring a magnet near it, and then I bring an electrically charged comb near it. Or glass rod or something, I suppose, right? Anything static. Which one induces a stronger tug? Well, you know, magnetism, it's not very efficient. You know, the magnetism induced into a non-magnetic conductor isn't strong magnetism. You know, so I mean, even if you drop a magnet in a copper pipe or something, it's not very much magnetism that's running through the copper to impede the progress of the magnet. So it's not like it's a very strong force. So, you know, and you're talking about, you know, 15,000 volts for the static electric charge on a comb, maybe. I mean, maybe that's high. You know, might be higher. And you're just moving an aluminum can. Well, the aluminum can is so thin that it's going to store a lot more charge, you know, because of its surface area. So charge is going to be more substantial than any magnetism you can create in it, because the magnet is only going to be affecting a tiny bit of the metal's density, where the charge is over the entire can is grounded, so it's the opposite charge of the comb. So, you know, in all likelihood. So yeah, that differential is going to be a lot stronger than any field effects created in the can. The amount of magnetism you create in an aluminum can is going to be just so tiny. I mean, it probably won't even make the can, you know, you have to take a pretty powerful neodymium magnet to try to get an aluminum can to move at all, I think. Yeah, so that's enough of that. So, yeah, so you know, eventually I'm going to go through this whole electrical thing, but I mean, it's just the idea, just follow the electrons. So wherever the electrons are going, just know the way they're moving, they're creating the red stuff is the stuff they're giving away for their movement. So their black force is moving them, and they're excreting red force to maintain their momentum. Yeah. And the protons are doing exactly the opposite in the opposite direction. But the field is moving in a direction. So it is, even if it's perpendicular, it's moving. Like the baseball on the bus, it does have two momentums. It has the speed of the electron plus the direction of the electron. It's really not the right way to say it. Yeah, so, yeah, forget I said that. I think the tendency is going to be that it just leaks some of the energy in that direction. I mean, because it doesn't, every time it turns to the left, it shoots it a little bit. Perpendicular is a little bit different angle, and the electron turns to the right, perpendicular is a different angle. That kind of problem. Yeah, it still doesn't get to it, though. Well, anyway, it doesn't really matter, I don't think. Point is, the key point is that if you think about a magnet, I guess I'll draw it this way, and a conductor, you just get the idea that there's going to be this red force coming, black force, sorry, out of the magnet. See, it is hard to, because it does switch. The two things change when it's electricity. They're opposites. The proton excretes black force. The electron excretes red force. But when they're in the form of a magnet, they excrete the same force that they're composed of. So that's what makes it a little bit confusing. But the electrons are obviously going to get, so this magnet would push the electrons and this way, and this would pull the electrons towards this direction. So obviously all the pressure would be in this direction, so the voltage would increase at this end. So wherever the voltage is just means there's extra pressure. And then when they're moving back, they're going to excrete essentially the opposite of what they pushed them there. They're going to give back what the opposite of what moved them is what they're going to excrete. If I can put it that way. So anyway, but yeah, there's lots of details to go in here. I'm just saying the principle is pretty basic, so I don't know why you have a problem with the principle that it's the magnetism is filtering the force. The filtered force is going to affect the electrons because of it's filtered. Okay. So it's probably enough. Let's see how much time. Oh, we got enough time. Yeah, so we'll do this real quick. So this guy, so he's part of this whole little group of people who all don't like conventional physics, but they all have their own sub-theory or replacement theory or unification theory. So him and his father are working on some unification theory that's basically some kind of variation on this Glenn Brokenart's whatever book that he likes, or whatever his theory about some things. Well, anyway, he's supposed to be the infinity guru. So his father's the particle guru. See, it's all kind of like a club of YouTube channels. So anyway, the idea of their theory is that, like mine, it's sort of particle. Okay. Anyway, so they start with the idea that gravity is a particle. But in breaking it, and then they have the same impression that this frequency thing is kind of messed up, waves and stuff. But they make a fundamental mistake in the sense that in getting rid of waves, they do it in 2 steps kind of a thing. So instead of just getting rid of it, just forget the idea of a wave and just deal with frequency. So what they essentially end up doing is saying, yes, gravity is this stream of particles. They call them G1 particles. So that's the basic particle. But the idea is he's calling it a low frequency stream. So the frequency is so low that it just seems like a stream. Well, the argument would be no, their individual path is all randomized, so there's no order. So they don't come at a frequency, any individual ones. So he's still thinking of them as almost like radio waves would be a blob of particles and a blob of particles and a blob of particles. He's thinking of making that a low frequency, and so he's just thinking too much in terms of blobs of particles instead of thinking that they're all individual particles. And that's all you need to do to get rid of frequency is just turn them all into individual particles, and then they'll lack frequency all on their own. So anyway, so then when he goes to make a photon, he ends up making the photon into a big blob of G1 particles. So there'd be like, whatever, I don't know, he doesn't say it, 100, 1,000, 10,000, 1,000,000 G1 particles in each photon, and the photons are essentially a blob of these G1s that are all collected together at a frequency. So that's the part that got right, is that the light is just quanta, is just particles at a frequency. And then the big mistake is he decides to eradicate electrons and make them into these G1 particles. And that's a huge mistake, because that gets rid of charge, that gets rid of polarization, And sort of as the previous conversation pointed out, polarization is hugely important. You know, kind of just really defines physics. It's what makes everything happen, is the fact that there's two kinds of quanta and two kinds of matter, and that they filter for each other. You know. So yeah, so his theory on electricity is just some, you know, kind of vacuous. Just, oh, there's a battery and it produces G1 particles. No explanation of how it stored them, how it releases them, anything. And they just push down the wire. And I can't remember what he said the electrons are doing. But he has this notion that the electrons just play along and go at the speed of light or something, and that's not what's happening. So yeah, so it wasn't. It lost all explanation because it just, like I said, you really can't get rid of charge. So their theory gets rid of charge, and charge is really important in physics. That's a fundamental function. The poles on the magnet. The electron is the magnetic monopole, the proton is the magnetic monopole, and when they're in relation to each other, they create a magnetic dipole. And that's really important physics. So anyway, so yeah, it just kind of goes nowhere from there. I mean, he has, you know, he had a little bit of an illustration of a radio signal, and it was really complex and didn't, you know, I mean, the conventional theory that the tons go through the atmosphere and vibrate a piece of metal, and the vibrations create electricity, makes a lot more sense than this G1 into frequency, and without, like I said again, without electrons to move current, it just doesn't make any sense. To provide the catalyst for the transfers. As I sort of pointed out before, the matter bits are critical just as catalysts. So a force can interact with a force, because the forces can't interact with each other. Magnetism can't interact with photons, let's say light. Can't make the two things interact until I put matter bits in there. Then the matter bits can react to photons and magnetism. So they're the catalyst, so forces can interact. Anyway, that's probably enough. It's interesting, that's all. Yeah, it was close, but they fell. Once you get off the rails on these kind of things, you know, yeah, it just doesn't go anywhere until you figure out what rail you fell off of. And you don't have the same luxury as the established physics, in that you just can't make up some new particle and give it a name and then make up some dark matter and just make up a Huygens and make up some other bullshit, because if you do it, you know, it's just making shit up. So yeah, you're just not given the same latitude. But anyway, there was something else that was relevant, but I don't know what it was, so I guess we'll give it a bye. I think, let's see, I don't think there was any other comment worth providing any argument to. No, I don't think so. Alright, so yeah, I have been soliciting a better audience, you know, sending emails to better physicists and see if they will, for some small cash prize, be willing to critique my physics. Let's see if we can get anybody to bite. So until next time, and such.